Okay, welcome back everybody. So in this video, we are going to find the interval and radius of convergence of the specific power series x minus 3 to the n over 2 to the n times n. And in order to find both of these, interval and radius of convergence, we are going to need to use the ratio test. So let's just keep it handy and rewrite what the ratio test would be. So ratio test is just the limit as n approaches infinity, c to the n plus 1 times x minus a to the n plus 1 all over c to the n times x minus a to the n. Okay, so the top portion is the n plus 1. We're just inputting n plus 1 into every n term, and the denominator is just the original power series that we're starting out with. So let's use this and then try to find the interval and radius of convergence. So uh, let's get to it. So solution, we'll say we'll use the ratio test. Okay, so using the formula for the ratio test. Okay, so this would be L, our limit that we're trying to find, equals the limit as n approaches infinity, x minus 3 to the n plus 1, all over 2n plus 1 times n plus 1 all over the original power series x minus 3 to the n over 2 to the n times n, and all absolute value. Okay, so we are dividing two rational terms, and so when that happens, don't forget to keep writing your limit. We reciprocate the bottom. So this would be x minus 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 times 2 to the n times n all over x minus 3 to the n. Okay, so we can use some algebra and properties of exponents to break this down a bit. So I could separate some of these exponent terms. So this could be x minus 3 to the n times x minus 3 to the 1 all over 2 to the n times 2 to the 1 times n plus 1 times 2 to the n times n over x minus 3 to the n. And absolute value. So now that we separated out some exponents, a couple of things could be canceled out. So that works out quite well. 2 to the n gets canceled out. X minus 3 to the n gets canceled out. And so what I'm left with, gonna come and bring it back over here. Okay, what I'm left with is an absolute value, x minus 3 to the times the n over n plus 1. Okay, so if you recall using ratio tests, there's one component we do within these problems is recognizing that this limit is discussing n. This limit has nothing to do with x. So we can essentially take out an x expression. So I'm going to take out x minus 3. Be careful, it's still absolute value. So it would be absolute value of x minus 3 times the limit as n goes to infinity, absolute value of n over n plus 1. So let me make a little note. I can take out the x minus 3 because has no n. Okay, so we then have the limit as n goes to infinity, n over n plus 1. And so, we could go off to the side here and say what that limit would look like. So the limit n goes to infinity, n over n plus 1. Well, if we plug in infinity here, we get infinity over infinity, right? And so we can use our friend L'Hopital's, take a derivative of the top and bottom, and we get 1 over 1. So the limit is just 1. Okay, so we did that using L'Hopital's. You can look at it, the ratio of the powers, the top and bottom. But yeah, so this whole thing is just going to be, let me say this just goes to 1, or let's say equal 1. Okay, so what we're left with is just absolute value of x minus 3 times 1, which just equals, okay, sorry about that. I saw a typo I made. I forgot about this 2 to the 1 right here. That carries along with it. So let me just rewrite a couple things, that this should be, you know, 1/2 essentially. And I can also bring out the 1/2 here, right? Because it's just a constant. So what I'm left with is just 1/2 times the absolute value of x minus 3 times 1. Okay. And well, that's just going to equal 1/2 times the absolute value of x minus 3. So therefore, that's what L is. 1/2 times the absolute value of x minus 3. Okay, so that's our limit. Okay. But we're still not done. We need to figure out the interval and radius of convergence. So for the ratio test, in order to converge, we need the limit to be less than 1. So what we're going to do is set our limit less than 1 and solve for x. So we'll have 1/2 absolute value of x minus 3 less than 1, and we're going to solve for x. So we're going to isolate x. So 1/2, we're going to multiply 2 to both sides. So x minus 3 less than 2. We're going to drop the absolute value. So it'll be x minus 3 greater than -2, less than 2. And we're going to add 3 to both sides. And we'll have x less than 5 and x greater than 1. Okay, so that is the interval of convergence. Okay, so let me box it here. Okay, but if you can recall from the ratio test, we typically check the endpoints. Okay, so we typically check for 1 and 5 to see whether they should be equal to or not equal to in the interval of convergence. So the way to do that is we plug in these x values into our power series and see whether it converges or not. So what we're going to do now is test the endpoints. Okay, so for x equals 1, all right, what we're going to do is plug that into the power series that we're given, that we're working with. So this would be 1 minus 3 to the n over 2 to the n times n. This would be the series n equals 1 to infinity, negative 2 to the n over 2 to the n times n. I can take out negative 1, the alternating component. That'll leave me 2 to the n. And so I could cancel out these 2 to the n's. And so what I'm left with is just negative 1 to the n all over n. And what is this? If you could recall from your calculus 2, this is an alternating harmonic series. And an alternating harmonic series, well, what that does is converge. Okay, so since it converges, I'm going to write this up again, but that means my 1 would be included in the interval, so it would be an equality. But I'm not going to write it right there. I'm going to write it up more in a final answer. So we got to do the same thing to x equals 5. So let's plug in 5 into our series. So it'll be 5 minus 3 to the n over 2 to the n times n. So this would be 2 to the n over 2 to the n times n. No alternating part to worry about. So what I'm left with is n equals 1, 1 over n. And what is that? That is a harmonic series, which always diverges. So what I could say is, therefore, x equals 1 is included and x equals 5 is not included. Okay, so we have our interval convergence. Therefore, the interval of convergence is 1 less than or equal to x, which is less than 5. And the radius of convergence, well, the radius of convergence is always half the length of the interval of convergence. So the radius of convergence, all you would need to do is take your endpoints, subtract them, and divide them by 2. So this would be 5 minus 1 over 2, which is 2. So therefore, the radius of convergence is 2. Okay, so the power series will only converge for x in the interval 1 to 5. Notice a hard bracket on 1, the parentheses around 5, with a radius of 2. So I'm going to circle this answer since that's like our final answer. Okay, so that's how you would find the interval and radius of convergence. So yeah, I went ahead and tested the endpoints to see whether they should be included or not included. Um, but the issue with that is these problems take too long anyways. So you don't need to check the endpoints. In the future problems that you're doing. Okay, so this was just me showing and reviewing a bit about testing for endpoints, which one should be included or not, but this isn't a big sticky point when we do these problems. So I just want to show you this one time so you kind of remember a little bit. But when you're doing these, you don't have to test the endpoints, okay? So just get your interval convergence, get your radius of convergence, and you should be good to go. And then once again, apologies for the typo. Yeah, I missed that 2 to the 1 here, so that kind of just carries around and helps us out in the final problem. So just keep track of that. Uh, Make sure to fix the mistake that I made, but that's it for this video. Thank you for watching. Bit review about ratio tests and interval and radius and convergence. We'll keep reviewing some power series moving forward. So I'll see you in the next one. Take care.